At GraphCore, we have built our IPU technology to be deployed at scale. This enables us to build scalable machine intelligence systems. In this presentation, we discuss our silicon, our platforms, and our software, and how this enables the current and next generation of machine intelligence applications to execute efficiently on GraphCore technology. What do we mean when we talk about scalable IPU systems? Our scalable IPU systems are built around three main GraphCore technology constructs: our silicon, our platforms, and our software. Our silicon is based around a multi-generational silicon architecture. This is designed to provide optimized support for high-performance machine intelligence applications and workloads at scale. Our first generation Mark I Colossus device is available today and available to use. In order to support deployment of our silicon, we have our hardware platforms. These are designed to deploy IPU devices efficiently. This enables optimized applications to execute on IPU in support of industry-standard deployment use cases. Our Dell DSS8440 platform is available to buy today and available to use. In order to use both our silicon and our hardware platforms, we have most importantly our software. Our software provides the glue between these other two technology constructs. Software provides support for common machine intelligence development frameworks and direct IPU programming. This enables developers to seamlessly integrate IPUs into applications. By combining these three key GraphCore technology constructs together, we produce scalable machine intelligence systems that can be built on top of IPU technology. When we talk about scaling, we first start with scaling on device. Our IPU is a massively parallel distributed processing engine designed for machine intelligence applications. The first generation IPU, Colossus Mark I, is built using 23.6 billion transistors. This enables 7,296 fully independent and fully programmable workers to execute utilizing 45 terabytes a second of memory bandwidth. Each device contains 300 megabytes of in-processor memory, a PCI Gen 4 interface, and an IPU link interface for connecting IPU devices together. In order to utilize the silicon, we have three main constructs which cross both hardware and software: compute, exchange, and synchronization. Compute is provided at the tile level on IPU. We have 1,216 fully programmable IPU compute tiles which can execute any application, including highly complex control flow. Each of these contains 256 kilobytes of in-processor memory, accelerated floating point hardware engines, and 6 independent hardware workers per tile. This compute capability allows us to run machine intelligence applications efficiently on IPU. In order to complement compute, we have our exchange capability. Exchange provides an 8 terabytes a second tile-to-tile communication fabric for tiles to communicate. It supports any communication pattern and is fully timing deterministic in its execution. We know exactly how long it takes to send a byte from one side of the chip to another from tile to tile. This allows us to build highly complex and optimized compiler support for the communication patterns. It is driven entirely by the software toolchain. When tiles communicate, the communication patterns are generated entirely by our software compiler. In order to facilitate the compute and exchange phases of an application, we also have highly optimized hardware-accelerated tile synchronization logic. This allows the low latency messaging of work completion. It is used to move between compute and exchange phases in software. As with the exchange, this is also targeted by our software compiler, and we have a highly optimized and extended instruction set for synchronization on IPU. These three constructs perform the core capability to allow machine intelligence applications to scale on device. Along with scaling on device, we also support scaling across devices. Our IPU link technology enables us to connect multiple IPU processors together to provide a single software target made up of multiple IPUs. In our first generation silicon, we support connecting up to 64 IPUs together usable as a single large IPU from applications. This enables utilization of 466,944 fully independent workers and 19.2 gigabytes of in-processor memory. For a machine intelligence application, this leverages over 1.5 trillion transistors. In order to achieve this, we extend our key IPU constructs across devices. IPU exchange is extended across multiple IPU processors. The exchange model we use on-chip is extended across devices. This allows tile messaging between IPU devices and across systems. We have support for highly optimized cross-IPU synchronization, which also extends between IPU devices to enable the fast switching between compute and exchange, even when running with large numbers of IPUs. All of this technology is driven by our compiler support in our software toolchain. All of the communication and synchronization patterns are generated in software by the compiler with a highly optimized set of execution routines. In order to achieve this, we use our IPU Link technology to enable device-to-device connectivity. IPU Link provides 320 gigabytes a second of IPU to IPU bandwidth and supports communication between IPUs. Its layout and configuration is fully software configurable into the shape and size of the networks we build. It supports point-to-point tile messaging and through routing between processors for efficiency. In order to present this to software, we create a software construct called a graph compile domain. This allows a single application to be programmed against a much larger group of IPU processors. It is fully configurable in its partitioning and allows us to allocate any IPUs to the graph compile domain. This enables both data parallel and model parallel execution for applications. These constructs and our IPU silicon technology enable us to build a system which supports machine intelligence applications scaling across devices. Along with scaling on device and across devices, we also support scaling across systems. This allows us to connect together multiple IPU devices for machine intelligence applications at massive scale. An example below is this 256 IPU application target built from interconnected 64 IPU domains. On our first generation technology, we allow the scale-out support of up to a maximum of 4,096 IPUs. In order to achieve this, we extend our key software and hardware constructs across systems. Our IPU exchange technology is extended to be supported across domains. As with on-device and across-device support, across systems this is also supported by our compiler. Our highly optimizing graph compiler generates the communication primitives and patterns that go between systems as well as between devices. This enables us to implement efficient application collective support and allows us to scale up to 4,096 IPU devices. There are two ways in which we can scale across systems. Firstly, IPU Link. IPU Link can be extended across domains and support optimized IPU Link collectives. This allows us to support replication across highly optimized IPU Link connected systems. It supports the standard IPU software model of compute, exchange, and synchronization. All of this is supported by our software compilation technology, enabling optimized communication patterns to be generated between systems. Along with IPU Link, for standard server platforms, we also support PCI Express-based scaling. IPUs have the capability to access both memory and devices on the host system over PCI Express. This allows us to interface efficiently with host-based software. Applications can build on top of host networking support and support the scale-out of applications in standard server architecture platforms. The combination of these constructs and our software support allows us to build optimized machine intelligence applications that scale across systems. In order to support applications on IPU, we designed a very simple execution model. This execution model is based around computational graphs. It extends through our silicon, our hardware platforms, and our software. Computational graphs are built around some simple constructs. Data, which is being processed by the graph, vertices, which perform the processing, and edges, which define the communication pattern between the data and the processing vertices. In this example on the left, you can see a very simple computational graph. 4 elements of data are passed to 2 parallel adder vertices. These add the data together and produce 2 outputs. The same adder vertex is used to produce a final output. This shows a simple reduction with an addition operation. All machine intelligence applications can be shown to use computational graphs, including control flow. In order to map this to the IPU, we use a BSP schedule. This bulk synchronous parallel schedule enables us to utilize our silicon exchange and compute capability efficiently. The software maps the computational graph onto this schedule. As you can see here, The schedule for exchange and compute is broken up by synchronization primitives where necessary. The exchange shows the transition of the edges between the data and the vertices in the computational graph. The compute phases is the actual execution of the compute. This simple model allows us to efficiently execute applications on IPU. Once we generate an optimized IPU execution schedule, we execute it on the processor. This trace on the right-hand side shows output from our POP Vision graph analyzer. Its BSP execution trace capability enables you to see all of the execution on all of the IPU tiles. In this example, we see starting from tile 0 to tile 1215, execution of compute and exchange phases as we move forward in time. This execution model extends through all of our software and is the basic building block for all of the application support on IPU. In order to enable scalable machine intelligence applications, we utilize our POPLAR SDK. Since its first production release in September 2019, we have moved forward very quickly with its functionality and capability. It is split into three main components. Firstly, the machine learning frameworks. In order to support application developers and machine intelligence applications, we have to support the standard machine learning frameworks. Currently supporting PyTorch, our recent work with Baidu on Paddle, and an Onyx interface, these three go through what is our POPLAR advanced runtime in order to target the IPU. Along with these, we also support TensorFlow and have a highly optimized XLA backend that targets the IPU processor. The combination of these machine intelligence frameworks allows us to support the wide majority of applications available today and enable the research into the applications of tomorrow. Secondly is POPLAR. POPLAR is core to the IPU software development platform. It contains several key elements. Firstly, the standard libraries, supporting common application library interfaces that are required for the machine intelligence frameworks, such as matrix multiplication and convolution, various operations for graph execution, random number generation, and communication collectives that operate between IPUs and between systems. These all build on top of the graph compiler and the graph engine, performing the core runtime capability of the POPLAR platform. POPLAR is abstracted from the underlying hardware via its device interface. This device interface sits on top of our driver software stack. This abstracts away both our PCI-based systems and our IPU fabric-based systems from the host in order to provide a single POPLAR application target. The combination of the machine learning frameworks, POPLAR, and our driver software stack enables efficient execution of machine intelligence applications on IPU. Along with our POPLAR SDK, we also have other key software constructs. Most importantly, our ability to target multiple IPU devices from applications. This is split into three parts. Firstly, model sharding. Model sharding supports the splitting of models across multiple IPU devices. In the diagram here, you can see two IPU devices being used to implement a single model with communication between the IPU devices themselves forming part of the model. This allows user-driven software control of model parallelism. Alongside model sharding, we also support model replication. In this diagram, we can see the same example that is sharded being taken and replicated across an entire system. By inserting collective operations, we enable data parallel training and the automatic replication of models. Thirdly, model pipelining. To support the efficient use of IPUs, we also have key constructs for model pipelining. These are designed to extract maximum performance from model parallel execution. With this, we can form complex pipelines between multiple IPUs in multiple systems. All these constructs are fully supported in PyTorch, TensorFlow, PopArt, and POPLAR today, and form the core capability to enable scalable machine intelligence applications on IPU systems. POPLAR, from which the POPLAR SDK takes its name, is the core software technology used for programming IPUs. It consists of three main components: the graph library, the graph compiler, and the graph engine. The graph library is a simple C++ graph building API. This allows the specification of computational graphs for execution on IPU. It supports the execution model described earlier for IPU devices. This allows users to implement any application, including full control flow, and program the IPU directly. It is also used as a target for the machine intelligence frameworks to talk to POPLAR. This seamlessly integrates POPLAR with systems such as TensorFlow and PyTorch. Along with the graph library, we have our optimizing graph compiler. This is built to implement the IPU execution model. It takes the computational graph described in the graph library and maps it to the IPU machine underneath. This allows an efficient execution of applications using the IPU BSP execution model. For code generation, we build on top of standard compiler support in LLVM. This is used for our application compilation and our binary generation. Once we have compiled an application, we have to execute it. This functionality is provided by the Graph engine. This provides us with a high-performance graph runtime for interfacing with the host system. It allows efficient utilization of host memory and transfer of data between the IPU to the host system. This interface is highly optimized and provides key application capability for performance. The combination of these three components provide our POPLAR support. POPLAR is also now extensively documented on our developer portal, enabling a comprehensive user guide for the POPLAR API, how to use multiple IPUs in applications, tutorials and code examples for programming directly at the POPLAR level, and a detailed description of the underlying concepts. POPLAR is an important framework for programming IPU, and we continue to improve its support. Along with the core POPLAR capability, its graph library, its graph compiler, and its graph engine, we also provide a set of optimized POPLAR application libraries. These contain over 50 optimized functions for common machine learning models, built on top of more than 750 high-performance compute elements. The POPLAR libraries, in conjunction with the POPLAR graph compiler, enable machine learning frameworks such as TensorFlow and PyTorch to target IPU efficiently. The POPLAR libraries themselves are split into several subcomponents. POPNN for functions used in neural networks such as pooling and loss functions, POPLIN for linear algebra such as matrix multiplication and convolutions, POPOPS for performing element-wise operations on tensor data, POPRAND for populating tensors with random numbers, POPUTIL for utility functions for building graphs on IPU, and GCL, our optimized collectives library supporting model and data parallel. These 6 libraries integrate with POPLAR to provide a full platform for programming IPU. The POPLAR libraries provide optimized work planning of functions across IPU devices. They map the functions required to the IPU underneath efficiently. Below you can see output from 4 separate matrix multiplication operations at the POPLAR graph IR level. We specialize every operation based on its input and output for efficient execution on IPU devices and maximum performance. This is a core capability of the POPLAR libraries. Alongside the application functions, we also provide extensive documentation for the use of the POPLAR libraries on our developer portal. This, combined with the POPLAR documentation, allows people to program directly at the POPLAR level efficient applications that run on IPU. The POPLAR libraries are integrated into the standard machine learning frameworks along with POPLAR to provide application-level support for programming IPU platforms. In order to enable scalable machine intelligence applications, we support the common machine learning frameworks. TensorFlow and PyTorch have been heavily extended and optimized supporting IPU devices, including support for our MULTI-IPU constructs. With TensorFlow, we support IPU as a familiar target for developers. You can easily move a GPU model to an IPU using our TensorFlow support. We have a fully performant integration with TensorFlow XLA, enabling an optimizing compiled backend for TensorFlow to target IPU directly via POPLAR. We support version 1 and 2 with examples and documentation. On our GitHub page, you can see examples of using TensorFlow for IPU today. With PyTorch, we enable native support for IPU with very simple extensions to allow us to use our MULTI-IPU constructs. This takes native PyTorch models and allows them to deploy and train on IPU devices. As mentioned, support for our multi-IPU primitives from PyTorch models is built into the core platform. Alongside TensorFlow and PyTorch, we also provide the POPLAR Advanced Runtime for inference and training, a highly optimized, lightweight runtime that allows deployment at scale. It supports ONNX model input and Python and C++ model building. It is an optimized and lightweight application runtime for deployment. The combination of these three machine learning interfaces allows us to cover the wide range of scalable machine intelligence applications. Alongside the frameworks themselves, we also have our developer portal providing key documentation and core capability demonstrating how to use IPUs from machine learning frameworks. This is available today and available via our website. Along with supporting the standard machine intelligence development workflows, we also support the standard software ecosystem for deployment. New hardware technology is very difficult to deploy if it cannot work seamlessly within this software ecosystem. We start with our standard PCI Express driver. This is provided in source form with our POPLAR SDK. It supports Linux and Windows and provides the full execution model required for these platforms. We also support virtualization and security. The IPU has been designed to execute seamlessly within virtual machine environments. This is supported today in Microsoft Hyper-V. For containers, we support Docker. The IPU software stack and driver layer fits seamlessly into Docker without modification. This allows customers and users to deploy with Docker today. On top of that, we also fit into the standard Kubernetes execution model. This allows orchestration of applications to be deployed on IPU devices. For deployment today, IPU is available in Microsoft Azure. This builds on top of all of these key capabilities for a standard software ecosystem. On our developer portal, we also have extensive documentation of how to integrate IPUs into platforms such as Docker and how to use them today. Our current POPLAR SDK supports full deployment and full use of Docker containers. Most important to GraphCore are our developers. Today we have close to 1,000 users signed up to work with GraphCore technology. Since our first production release of our POPLAR SDK in September 2019, we have made huge progress in the amount and the quality of the information available to developers. We recently launched our GraphCore developer portal. This contains all the information required to build next-generation machine intelligence applications with POPLAR. It provides extensive documentation, tutorials, video walkthroughs, and examples of using IPUs in applications. Alongside this, we have our GitHub site. Our GitHub site contains the application examples, tutorials, and benchmarks required to see how to utilize IPUs in applications. Both of these websites are available today and visible to users. The developer portal supports four main areas: the POPLAR SDK, use of our Pop Vision tools, documentation, and application examples. The POPLAR SDK documentation now demonstrates how to use all of the existing machine learning framework interfaces for IPU. It also contains extensive documentation on POPLAR, the POPLAR libraries, and its API. This enables the use of POPLAR as a direct programming framework. On top of this, it also documents and describes all of the tools that the GraphCore driver layer software provides for machine execution, including Docker. Our Pop Vision tools have been recently introduced to give profiling capability for applications deployed on IPU. These provide an extensive set of functions which allow optimization of IPU applications. Again, like the POPLAR SDK, there is extensive documentation on their use. As far as the documentation for developers, this has now been expanded massively since our first production release. You can find information on programming the IPU, programming in POPLAR, using TensorFlow or PyTorch, using our multi-IPU constructs, or deployment use cases. It also has how to use videos and application guides. Along with the documentation, we have comprehensive application examples of how to map applications to IPU devices. This is fully available on our website with walkthroughs and tutorials. As mentioned, developers are hugely important to GraphCore, and we continue to improve our developer support. In summary, you can see that GraphCore is making rapid progress with its platform capability for scalable machine intelligence systems. Some of our recent news articles show this exactly. Recently, we discussed joining Baidu's Paddle hardware ecosystem for supporting more machine intelligence frameworks, new releases of our POPLAR SDK and our POP Vision development tools, our work with Imperial College on accelerating next-generation computer vision problems, releasing our documentation and our developer portal, working with Microsoft on medical imaging for ResNext 50, and working with Quant for accelerating their image recognition for search tasks. We are close to 1,000 users of our POPLAR SDK and growing fast. It continues to evolve at pace with new features and new functionality. Our developer portal makes using IPUs simple and contains extensive documentation and tutorials on using IPUs at scale. You can try IPU today in the Microsoft Azure cloud. For further information, please visit our website. For more details on our POPLAR software stack, our IPU products, our IPU systems, and our developer documentation and application examples. Thank you.